Oh, maybe it was already recording and I didn't notice. Welcome everybody to this week's GOCC. It's great to see all your lovely faces. We have a great speaker today, but before we get started, let me just remind everybody of our community statement. And we kind of follow three guiding principles. And the first is that we are all learning. The pandemic has forced us to change the way we kind of do math and learn and all this stuff. So we need to just be patient with each other. This is partly a research/learning seminar. The second thing is that everyone has something to contribute. And so we all approach combinatorics a little bit different. And so if you have connections to the things that the speaker is speaking about, please use the chat, share ideas, connected, maybe some papers. And then the last one is that no one has all the answers, not even the speaker. So if there's something that is interesting, maybe we can try to figure it out, or somebody has a resource or somebody that we can talk to, please share that. But let's just keep that in mind. And yeah, so with that, it is my absolute pleasure to introduce my dear friend Max Hlavacek, who is a PhD student at UC Berkeley and was at FU Berlin exactly a year ago, I think, right, Max? When I visited.
Yeah.
And so
that's where I was.
Yeah, and so Max will be talking to us about order polytopes of signed posets. So let's welcome Max.
Hi, thank you so much, Andres, for introducing me. And thank you so much to the organizers. And thanks for all of you for coming and listening to me babble for a little bit. So I'm going to be talking about order polytopes of signed posets. And this is a project that I'm working on with my advisor, Matt Beck. Oops. Okay, sorry, okay, there we go. So I just want to go over a little bit about what's to come. So first I want to introduce what an order polytope is. And then I want to talk a little bit about what signed posets are, which Reiner introduced in 1993. And I know that some of you are Reiner students, so you might be more of an expert on this than I am. So I'm excited to hear your input. And then I want to talk about how I constructed order polytopes of these signed posets. And then what questions should we ask about these structures now that we've created them? Have we just created them for no reason, or are there some certain questions we can ask about them? And throughout this talk, I would really want to highlight that I think that this topic goes into some algebraic concepts that I don't know too much about because I come from more of a combinatorial and geometric standpoint. So please, please, please help me out. If you see any connections that I'm missing, please tell me. I'm excited to gain your wisdom today because this is an ongoing project. Okay, so first I want to introduce what a polytope is. So a polytope is what happens when you take a finite set of points in space and then just take the convex hull over it. So just kind of like cover them in saran wrap and you have this shape. And a lattice polytope is a polytope in which all of the vertices are integer lattice points. So since I am mostly concerned with counting lattice points inside of polytopes, I pretty much have only dealt with lattice polytopes in my life and not other polytopes. So now I want to kind of introduce what an order polytope is, because this is kind of the base structure that I want to build off of in this project. So an order polytope is a much studied object that comes from a poset. So a poset is a partially ordered set. So you have a bunch of points and then you have ordering between some of them. So here is my example poset, which is actually also a total order, but I can't really draw higher dimensional polytopes very well. So we just have this. And the order polytope is what happens when you give a coordinate to each of the points in your poset. So for point 1, we have x1, and for point 2, we have x2. And then the polytope is the set of all points such that, first of all, it lives inside of the unit cube, and kind of the ordering of the coordinates respects the poset. So since 2 is above 1 here, we want all the points such that x2 is greater than x1. So the order polytope corresponding to this poset is just this triangle right here. Does anyone have any questions about that construction? Alrighty. So one really cool thing about this is that inside of this shape, there was a lot of information about your original poset encoded. So this is kind of like a geometric representation of your poset. So first of all, you can see in the previous example, we had a poset on 2 elements, and the order polytope had dimension 2. So the dimension of the order polytope, and this O of pi is notation for the order polytope that I'll use, is equal to the number of elements in your original poset. And then there's a few other things. I highlighted these words in pink because not everyone may be familiar with them. So I'm not going to totally formally define these words, but we can kind of talk a little bit about what they mean. So the vertices of the order polytope correspond to the filters of your poset. So the filters are just a subset of the poset that's closed upward. So for example, if you include this middle point here, you would also have to include the top point. So that is a way of encoding the vertices of your order polytope. The facets, which are the highest dimensional faces of your polytope, so for example, the facets of a cube would be the 6 squares, correspond to the cover relations of the poset and also the maximal or minimal elements. So you can see from this poset that there's going to be 5 facets, 1 coming from this top element, 2 coming from these 2 minimal elements, and then the cover relations are just the relations that are represented by a line in this diagram. So then you have this, a facet coming from this line, a facet coming from this line, and a facet coming from this line. Also, can you all see my cursor? I always get confused whether or not. Okay, perfect, thank you. And then kind of most exciting to me is that you can actually find the volume of this shape by counting the number of linear extensions of your poset. So a linear extension of your poset is kind of a way of flattening out your poset into a total order in a way that respects the partial ordering here. So for example, one linear extension of this poset will, I take this one, and then I take this one, and then I take this one, and then I take this one. So basically, I couldn't take this one and then take this one because this one's below this one. All right, so to me, that's pretty cool, the fact that all of this information is encoded in the order polytope. But there are a few other reasons why people care about order polytopes. One is just that it's kind of a good combination of simple and complicated. So for example, we know all of those facts about the order polytope coming from the poset, but there's still some complications, such as the volume is computationally hard to compute because the number of linear extensions of a poset is computationally hard to compute. So there are some like complicated things still here. And kind of the reason why I like order polytopes is that they serve as like a nice combinatorially defined entry point to some open problems. So I am in Earhart Theory. So I'm going to introduce one of the open problems in Earhart Theory that order polytopes can kind of serve as an entry point to. Maybe not so successful. I don't know if it's a successful entry point because this problem is still open, but we'll see here. Okay, so I want to talk a little bit about what Earhart Theory is. So we're going to take a brief detour through the world of counting lattice points.
Can I interrupt you for a second just to make sure that I understand everything that's going on?
Yeah, please.
So one thing that I was thinking about, so if we take our original example from the beginning, that single line, then that gave us a triangle, right?
Yes.
But does it go on forever, or is it like a unit side length triangle, or?
Yes, should have labeled this. They said these things, it's like the intersection of kind of the hyperplane defined by the ordering. So this one
Okay.
with the unit cube. So they sit inside the unit cube.
Sits inside. So in this case, the unit cube is a square, right?
Yeah. So that's coming from this part of the definition that.
Okay, yeah, I see that
yeah.
now. But then the other question I had is that, so there's only one way to order this, which would make me think that this would have volume 1, because I think that there's one linear extension, but then wouldn't it have volume 1/2?
Really good question. So I think I should have said that there's kind of like a scaled volume measure. So so I think it's up to some kind of scalar depending on what dimension you're in.
Okay, cool.
Yeah, really good point. So I think you have to like multiply the volume by d factorial if you're in dimension d.
Yeah, makes sense. I mean, certainly you're never going to have a volume that is like a positive. I mean, you're never going to have anything bigger than 1. So
yeah, yeah, that's a good point. And then Andres put in the chat that this is called the normalized volume, which is the word I was looking for, but I couldn't get it out. So thanks, Andres.
Cool. Thanks.
Thanks so much for your questions, Alex.
Yeah.
Any other questions before we go?
Yeah, I have another question. So is it the case that each point in the order polytope corresponds to an extension of the posets to the linear order on the the numbers from 0 to 1?
That's a really good question. So it turns out that you can kind of divide your order polytope into triangles. In this case, it's not very exciting because there's just one triangle, but let me go ahead a little bit. So this is not an order polytope. It's a signed order polytope because you can see it doesn't fit in the unit cube, but you can see it's divided into 2 triangles, and each of these triangles corresponds to a linear extension. So that's kind of how I think about how the linear extensions show up in these objects.
And then, yeah, I think there might be a similar question in the chat. Is the volume of order polytope is related to the number of linear extension, as you mentioned in the third slide?
Yes, thank you so much. So the volume of the order polytope is the normalized volume of the order polytope, which is a scalar multiple of the volume depending on the dimension, is exactly equal to the number of linear extensions of the poset.
Well, no, what I was had in mind is that when we say linear extension of a poset, we first think of an extension of the poset to the integers under the standard order. But one can also think of a linear extension of the poset to real numbers.
Oh,
And so a point, a tuple in R pi corresponds to a sequence, a real number for each element of the poset. And in these real numbers are between 0 and 1. And then the order of course, they're linearly ordered. Or there might be 2 of them that are equal, but they're linearly ordered, and that linear order is an extension of the poset order.
Oh yeah, exactly. Thank you so much for, yeah. Sorry for interrupting you.
I think that was his whole comment.
Awesome. Thank you. Yeah, for that comment. So you can think of each point that's a really good way of thinking of the order polytope. Thanks, Seth. So you can think of each point in the order polytope as like kind of a series of numbers that respects the order, at least weekly, of the poset. Thanks so much. Any other questions before we start? We take a little detour. Awesome. Thank you, Galen. So we're now going to take a little Earhart Theory detour. So now it's kind of confusing because poset and polytope both start with P. So if you're confused about what the P stands for at any point, please let me know. But here, P is going to stand for a lattice polytope. And I'm interested in counting the number of lattice points in that polytope, but I'm also interested in how that number of lattice points changes when you dilate the lattice point. So for example, for this square, first there's 4 lattice points, but if you double it, then there are 9 lattice points. And then if you triple it, there's 16 lattice points. And you can kind of see that there is a polynomial that can give you 4, 9, and 16. So more generally, the Earhart polynomial of a polytope, when you put it, is a polynomial in N, which Earhart proved in 1962, and it counts the number of lattice points in the nth dilate of your polytope. Oops. Sorry, I keep accidentally clicking. And the Earhart series is kind of the generating function where you have a power series in Z, and the coefficient of Z to the N is the Earhart polynomial evaluated at N. And so you can write this series as a rational function with the denominator 1 minus Z over D plus 1, and that gives you a D plus 1 degree polynomial in, actually it should be D, there's a typo here. This gives you a D degree polynomial in the numerator. And we call, we call this the H star vector of your polytope. The K's here should be P's, sorry, typo. So the reason why sometimes I talk about the H star polynomial instead of the Earhart polynomial, I think of it as a change of basis. It encodes the same, exactly the same information, but the H star polynomial satisfies some nicer properties in the Earhart polynomial. For example, for a polytope, the H star polynomial, all the coefficients are non-negative integers, which is not true about the Earhart polynomial. So that's why we care about the H star polynomial. So when you have a really nice sequence of numbers, such as the coefficients of the H star polynomial that are all non-negative and all integers, you might ask if it satisfies some other properties. So one of those really big properties that people like to ask about is unimodality. And that just means you go up to a certain point and then you go back down. So for example, a lot of the polynomials that we know and love have unimodal coefficients, such as the binomial expansions. Those go up and then they go back down. So a big question in polytope in Earhart theory is, do blank have unimodal H star vectors, where blank is a nice family of polytopes? So there are several things the blank could be. So some possible candidates for the blank are IDP polytopes, which are polytopes that satisfy this really nice kind of decomposition property. Polytopes that admit a unimodular triangulation, which means you can divide them into triangles that are as small as possible. And order polytopes, which I just defined to you. So I want to make a point here that this is a really big class of polytopes. This class of polytopes that admit a unimodular triangulation sits inside of this big class, and then order polytopes is the smallest class here. It sits inside polytopes that admit a unimodular triangulation. And all of these questions are still open, even for order polytopes, which we know a lot about. We don't know whether the H star polynomials of these polytopes always satisfy that up and down property. So you can see that I put a pink blank here. And this pink blank, you may guess, is where I'm going to insert signed order polytopes. So signed order polytopes kind of encompass order polytopes and also admit a unimodular triangulation. So I think the most ambitious the most ambitious way that this project could go is seeing if maybe there are some special family of order polytopes that satisfy this unimodality question. But first, we should define these objects and then maybe ask a few more basic questions. Yeah, and I don't really know. And just to be clear, I have not started thinking about that at all. But that's kind of like why this is interesting to me, because slightly broader than order polytopes, but you never know. Sometimes broadening things slightly makes it slightly easier to find like a nice family that satisfies the property you want. Okay, so now we are going to finally define what a signed poset is. So we have defined the first half of my title, so it's now time to define the second half. So first, I want to talk a little bit about some Coxeter notation, because what we're really going to do is we're going to talk about classical posets, talk about how we can redefine them in terms of Coxeter notation in type A, and then extend that to type B to come up with signed posets. And this is what Vic Reiner did as his PhD thesis. So first, I just want to say that phi will denote the type A root system here. And the type A root system is the set of points ei minus ej in Rn, where these are the unit vectors, and I and j are not equal. And then one thing that will come up is the idea of a positive linear closure of a subset of the root system. So if we have a subset of this root system, for example, E3 minus E2 and E2 minus E1, if we take this closure, what we're doing is kind of adding them up in non-negative ways, and then collecting all of the points that are also in the type A root system that we get. So here, if we add these two, we get E3 minus E1, so that would also go in the closure. And you might see that this might be related to some kind of transitivity property. Okay, so in 1993, Reiner gave a description that relates, that gives a one-to-one correspondence between posets on N and subsets of the type A root system on N that satisfies a certain number of properties. First of all, if you have a root in there, you can't have the negative version of that root in there. And then also, it's already closed. So the positive linear closure of it is itself. So I'm gonna kind of explain to you how this one-to-one correspondence works. So we have this poset here, and from each of the relations here, we're going to come up with a root. So since 4 is above 3, we're going to put E4 minus E3 in there. Since 3 is above 1, we're going to put E3 minus E1 in there. And since 3 is above 2, we're going to put E3 minus E2 in there. But those were just the relations that show up in this diagram. 4 is also above 1, so we put E4 minus E1. And 4 is above 2, so we put E4 minus E2. So we can see that this positive linear closure property corresponds to the transitive property of posets. So that's how you can view any poset as a subset of the type A root system that satisfies special properties. So you can also kind of think about how you can express the order polytope in terms of, so if someone just gives you these roots and doesn't give you this picture, you can still very easily write down the order polytope by intersecting the standard unit cube with a bunch of half spaces, where each half space is all of the points, such that when you take the dot product with each of the roots, you get something that's non-negative. So we're now intersecting a bunch of half spaces and the unit cube to get the same order polytope we did as before. Does anyone have any questions about that? All right. So now we're going to have the type B root system. So the type B root system is, we still have the same points as before. We have EI minus EJ, but now we can have EI plus EJ, minus EI plus EJ, minus EI minus EJ, and we can also just have plus or minus EI. So we've added a lot more points here into our root system, and signed posets are, we have the exact same definition as regular posets, except now we're in the type B root system. So that's why I think viewing posets in a Coxer perspective makes it so now you can extend this definition to any root system. So here's an example of a signed poset. So now we can have all sorts of weird things like E1 plus E2 and E2. Negative E1 plus E2 could have already been in a regular poset. So I'm going to represent these signed posets with kind of these double signed graphs. So I'm going to represent E1 plus E2 as a line between E1 and E2 with plus plus. And then I'm also going to represent E2 by just a loop around point 2 that's labeled with plus. Okay, so I want to give some comments. So I think if you are familiar with posets, you know that there's a minimal representation, which is given by those diagrams of them that you always see. So there's also a minimal representation here, but it's a little bit harder to see immediately. But here you can see that just given the first two, if you have E1 plus E2 and negative E1 plus E2, if you add them together, if you take 1/2 times this one plus 1/2 times this one, you get E2. So this thing is actually kind of redundant, but we will keep it there for fun. Okay, so now we can define an order polytope in kind of the exact same way that we did in the type A version. So now we're going to intersect a cube, but we're not going to intersect the unit cube because that kind of cuts out all of the fun that happens. We're going to intersect the -1, 1 cube with half spaces given by the dot products with the roots in your signed poset. So here P is a signed poset, not a polytope. Sorry about the confusion. Okay, so I shouldn't define a polytope and not give you a picture. So here are 7 pictures of signed order polytopes. So these are all of the ones up to rotation that happen in dimension 2. So I want to point out that these 2 are the only order polytopes in dimension 2, and here we have a bunch more. So that was exciting to me. So I want to talk very briefly. So if you recall the order polytope, you could connect the vertices to the filters of the original poset. So here you can't really connect the vertices to the filters of the signed poset, and Reiner gave a definition of filters, but you can say that the poset is a convex hull of these points. So these points here represent all of the signed filters of the signed poset that gives rise to this signed order polytope, but you can see that this isn't a vertex. So if you take all the filters, you get some kind of redundant points.
Is there like any way to know about the points that are in between? Like which ones might, like, is there some sort of property that might characterize which ones are the vertices, like beyond filters, or?
That's something I would love to find out. So thank you for asking that question. If anyone has any ideas, let me know. So I've thought very briefly about that and nothing immediately jumped to my mind, but I would love to think about that more.
Excuse me, I wonder if you could quickly go back to the slide with the definition of the signed order polytope.
Yes, if I can figure out how to work this.
Yes,
Yes.
like there we go. Thanks. Yeah. So alpha. So alpha is a unit vector, is one of the coordinate vectors.
Alpha is one of the possible sum of course. So alpha, let me go back, is a member of the type B root system. So it could be anything that looks like.
Okay.
So the half spaces are either going to like look like maybe like this, or they're just going to be diagonal like this.
Okay.
Yeah. But you're right, they definitely follow a very specific form. And I see in the chat that Galen wrote that there is a presentation of a signpost set which is symmetric around 0. So is that the presentation in which it's on like 2n+1 points?
Yeah. Sorry,
Yeah.
We can talk about this at the end. I was just like, when this vertices question came up, I sort of long wondered. Yeah.
No, that's a super good, because I found this later after I was thinking about the vertices, so I should definitely go back and think about this, if this representation gives any ideas there. Thank you so much. Okay, I'm already feeling so much wisdom from all of you, so thank you. And then I also wanted to talk about the facets. So the facets in this case, come from a minimal representation of the signpost set. So as I described above, this plus here is redundant. And you can see that the 2 plus would come from a hyperplane that's like this, and then you would shade up. So you can see that that doesn't define a facet, but these two lines define this facet and this facet. And then there's one more facet. This facet comes from this point in this representation that is all pluses and there's no minuses next to it. So that's kind of where you would get the facets using this representation of your signpost set.
There's a question in the chat. So Colin asks, so if signed posets can be seen as special types of posets, the symmetric ones, would that mean that the collection of all H star vectors of signed posets is equal to the collection of all H star vectors of posets?
That's a really good question. So I think, so the signed posets can be seen as a special type of posets that are symmetric about 0, but then the order polytope, the signed order polytope is not the same as the order polytope of that special poset, because that kind of representation is like adding a whole bunch of other points to encompass the signed information that's held here. So for example, for this poset, this representation would have 5 points in that representation of the poset. So the order polytope of that poset would be some 5-dimensional polytope, and this is just a 2-dimensional polytope.
Thanks, that makes sense.
Awesome. Thanks so much for your question, Colin. Okay, let's see what's next. So that leads right into what I wanted to talk about in the last 10 minutes of this talk. Oh, and just the organizers, does this end at 10:50?
It's sort of up to you, essentially. Generally, we hope it'll end at around that time, and then questions. You've got a lot of questions before, so I think if you went slightly longer, that'd be totally fine. But it's really just how long you want to go.
Awesome.
But keep in mind that some people might need to leave at the start of the next hour. So.
Yeah, I might also need to leave because I have a meeting with Sampada, who is here. All right. So thank you very much. So Colin asked a question about the H-star polynomial. So in the classical case with just regular old posets and their regular old order polytopes, there is a way to come up with the H-star polynomial that involves finding the Jordan-Holder set elements, which I will define later, and use descent statistics on those Jordan-Holder set elements. So it seems, well, I guess I have shown that this works for the signed order polytope as well, except instead of using the descent statistics of the regular symmetric group, we're going to use the descent statistics of the type B symmetric group. So I'm going to walk through how this works for signed posets. And if you're interested in how this works for your classical posets, let me know and I can refer you to a reference. So this is the running example we're going to use. So we're going to use this signed poset, and I'll show you a picture of the polytope later. So we just have two set elements in the root system. So E1 plus E2 and then E2. Okay, so the element of the Jordan-Holder set, some people think of these as linear extensions. Some people say that these are the inverses of linear extensions. It kind of depends on who you are, but you can think of these basically as linear extensions. So they are kind of in this case, they are ordered n tuples such that 1 through n, or plus or minus, the entries are all plus or minus 1 up to plus or minus n. None of the entries are repeated, and for all numbers from 1 to n, exactly 1 of plus or minus n appears in the n tuple. And lastly, the most important thing is that it's order preserving, which means that if you take the dot product of your n tuple with any of the roots in your signed poset, you get a non-negative number. So that is a lot of words. So let's see how this works for this example. So the linear extensions here are negative 1, 2, 1, 2, and 2, 1. And you can see that this plus here means that the second coordinate has to be positive. And then this line here means that if you sum the coordinates, it has to be non-negative. And you can see that all of these satisfy this. And then all of the other points like this that you could get will not satisfy this. So we're going to view these as signed permutations later. So we'll talk a little bit about what that means. Okay, so as I hinted earlier when Seth asked a question, we're going to use these Jordan-Holder set elements to build a triangulation of our order polytope. So this is the order polytope of that same signed poset from last time. And you can see that we can divide it up into 3 triangles. And in fact, these triangles are the smallest possible triangles you can get. So if you're fancy, you can call them unimodular triangles. So that will be helpful later. And you can see that, for example, I labeled this triangle with negative 1, 2, and that's because it's described by this set of inequalities. So 0 is less than or equal to negative x1, which comes from the negative 1, which is less than or equal to x2, which comes from the 2 here, which is less than or equal to 1. And you can see that I labeled the other triangles similarly. So does anyone have any questions about how I use these Jordan-Holder set elements or linear extensions to build this triangulation? All right, so when I compute H-star polynomials, I like to use half-open triangulations, half-open unimodular triangulations, because I do not like to use inclusion-exclusion. So one kind of really nice setup that you can use to decompose this into a disjoint union of simplices or maybe partially open simplices that are maybe missing a facet is this kind of visibility construction. So in this case, I'm going to pick just the point that is 1 through n scaled down so that it fits inside here. And then if I can see the outside of a facet of any of these little simplices, I'm going to remove it. So for the simplex that it's in, I can't see the outside of any facet, so none of them are removed. For this one, I can see the outside of this facet from this point, so I'm going to remove it. And for this one, I can see the outside of this facet from this point, so I'm going to remove it. So then you can see that the collection of this half-open triangle, this triangle, and this half-open triangle, if you put them all together, you get the whole polytope, and you're not double counting any of those facets. And one fun fact is that the H-star polynomial of a simplex of this size, a unimodular simplex with the I don't know, k facets removed, is z to the k. And since this is a disjoint union, we can just add together the H-star polynomials of each of these half-open triangles to get the H-star polynomial of this whole polytope. So here, what would the H-star polynomial of this half-open simplex be? So we're missing one facet, so this is z. We're missing no facets here, so this would give us a 1. And we're missing one facet here, so this would give us another z. So you can see from this picture that the H-star polynomial of this polytope is 1 plus 2z. So now I want to talk about how we can use this labeling to come up with the this labeling here to come up with knowing how many facets are removed in each triangle. So we're going to use the idea of descent statistics. So depending on your goal, there's a lot of different ways to define descent statistics on the signed permutation group. So you can kind of think about that as the permutation group, but then some of the elements have a negative sign attached. So the one that we're using here is called the natural descent. And so the natural descent statistic gives you the number of times that the ith element is smaller than the element before that, the I-1 element. And we're going to say that the 0 element is 0. So let's just look at this example. And this is some notation in which I should have written this differently, but this is notation in which this 3 bar means -3 and this 2 bar means -2. So we have a descent here because we're starting from 0 and then we're going down to -3. So that's one descent. Then we're going up to 1. So that's not a descent. And then we're going down again to -2. So here we would have 2 natural descents.
Would there be, if the last one was a 2, would there be a descent from 2 to like 0, or is there not something like that at the end?
So really good point. So we're possibly counting a descent at the beginning, but we're not counting a descent at the end. Really good question. So if this was 2, you wouldn't have a descent back down to 0. Any other questions? Okay, so a fun fact here is that, as you see from this example, you can prove that whenever you have a descent in the labeling of your simplex, you will remove a facet in this half-open construction. So in this case, we have one descent here because we're going down from 0 to -1. And that's the only descent, so there's just one facet removed. Here, there's no descent, so there's no facet removed. And here, there's a descent going from 2 to 1, so we have one facet removed. So in that way, you can write the H-star polynomial as the sum of z to the number of natural descents of all of the sign permutations that are in the Jordan-Holder set of your original poset. And I do want to say that this only works if your signed poset has this triangle in it, because we're using this as our base point. But you can always rotate your signed poset so that this triangle will be in it. So for example, if this was flipped over, we could just move it back around. So kind of that is what I've been working on, coming up with how to write the H-star polynomial using descent statistics. So some questions that I'm thinking about that you all might have some helpful tips for me is another property that we look for in H-star polynomials is whether or not they are symmetric. So I have an idea that I'm trying to finalize for this based on the representation that Galen talked about, using this like big symmetric poset representation. So I have an idea for this, but I'm trying to work out the details, but let me know if you have any other ideas. I'd also really, this is the big ambitious question. I really want to know if there are any special families of signed order polytopes in which it's easier to answer the question. The big question is the H-star vector unimodal? And then lastly, Stanley defined order polytopes and chain polytopes in 1986. So chain polytopes is another, it's another polytope that comes from posets. So I also would like to think of an analog in the signed poset case. So thank you so much for your conversation and your attention and your comments. It was super duper helpful. And thanks to the organizers again.
Awesome. Let's thank Max for that amazing talk. Okay. I know we've asked a lot of questions, but are there any other questions?
So this is maybe a goofy question. Is there some like reasonable notion of a signed Stanley-Reisner ring? Is this like one of the things that, yeah.
That's a great question. So that's what I was talking about in that I don't know any algebra. So I don't really know what a Stanley-Reisner ring is, although I know that it's deeply related to this. So if you would like to chat sometime, I would love to.
Absolutely. Also, like the class that Vic Reiner is teaching right now is sort of like about some of the ideas that I think you're thinking about. Yeah. So a lot of people who are in your talk right now skipped that class to come to your talk.
Oh, sorry.
Are there any other questions?
Oh, that's super exciting.
Any other questions? I have a question if nobody else has questions. So I know that you've been asking, thinking about the H-star polynomial. Okay, two questions. One is do you have computational like evidence that these things are looking like they're going to be always unimodal?
I do not. That is something that I should run some code. Thank you, Andres.
I guess like people believe though that the IDP polytopes are, right?
Depends who you ask. I think
Okay.
There's no counterexamples.
I think it's a conjecture by Osugi and Hebe that if they are Gorenstein and IDP, then the H-star polynomial is unimodal.
Yes.
Yeah.
So if that is solved, then that would completely encompass this case. So, we're all kind of waiting to see.
So the Earhart polynomial of an order polytope is essentially the order polynomial of a poset.
Yeah, up to some kind of shift.
Yeah, up to some shift. Is there some notion like that for this signed business?
I don't know. I feel like if I was to define an order polynomial, I would just define it as this polynomial that I have.
Right.
But I should double check to see if anyone else has already defined a signed order polynomial, which might be in Vic's paper. I don't quite remember.
So yeah, so it might be interesting. I guess maybe you've already looked at what these Earhart polynomials are looking like, right? I mean, it's always nice for what you want to look at the H-star polynomial, but it might just be that these are already Earhart polynomials for what you want.
That's a good point. I always forget to just look at the Earhart polynomial before just going to the H star polynomial. Thanks, Andres.
I might have a question.
Yeah, go ahead.
So like, do you know 0-1 polytopes? So
Yeah.
like 0-1 polytopes, I think are like a generalization kind of these order polytopes. Do we know if there's like a nice like Earhart polynomial for those? And if so, is there like a signed version of those?
That's a really good question. So I know that like I've seen people talk about 0-1 polytopes, but I don't quite remember like what they have shown about the Earhart theory of those. And I would love to, I think, so this I guess would be 0-1 -1 polytopes, which I imagine some people might have also looked at, but I'm not sure. Thank you so much.
I have just like a clarifying question, or
Yeah.
I don't know if it's a clarifying question, but when you define the natural descent in type B, like how does that compare to the like Coxeter descent?
That's a good question. So I don't know which of so I've seen several descent statistics, but I don't know which one is the Coxeter descent statistic.
It's like the one where you look at the length, like you index the descents by the simple reflections, and then you say it has a descent at the simple reflection if you multiply it and the length decreases.
All right.
Could you go to the definition of the descent?
Oh yeah, sorry, I missed.
And I know it coincides, like it does coincide with a more combinatorial descent, but I can't remember if it's this one or if it's like a slightly different one.
Yeah, it's the same descent. They're
Okay.
they're identical.
Okay.
It's just this descent is when you're looking at the permutation version. So if you look at sign permutation, this is how to look at descents in type B. If you look at more like the word structure, so if you're looking at more of a group way of looking at the Coxeter group, then you would look at how you were describing for descents.
Thank you so much for that clarification. I treasure all connections that I can give this back to like algebra that I don't know.
To go back to Aram's question about Earhart polynomials 0-1 polytopes, I think Matt actually wrote a paper with Jesus de Loera, Richard Stanley, and some other peeps about this. And I think they computationally looked at 0-1 polytopes like in lower dimensions. So I don't think and like they bound some of the coefficients and the roots, but I don't think in general we know much about 0-1 polytopes and their Earhart theory.
Thanks so much, Andres.
These are all great questions, Max. I mean, I feel like it means people are engaged. Are there any other questions? Yeah, Galen put a paper in this thing. Yes, that paper. That's right.
Galen's always on top of it with papers.
Yeah. Oh, yeah.
I'm so impressed.
Julian Feifel. Yeah, that's.
If I
Okay, well,
ever need to find a paper, I'll email you. Just kidding.
Galen is a walking, talking math signet. If there are no other questions, before we thank Max one more time, let me invite you next week. Next week, our speaker is Kevin Marshall from the University of Kansas, and they'll be talking to us about a Hopf monoid on set families. And so please join us next week. I guess another announcement is next month we will be thinking about who will run the GOCC in the future. I know we've received some emails, but if you are interested in co-organizing the GOCC, as all three organizers are finishing their PhD, will no longer be graduate students, we would like for this to run. So please send us an email if you're interested. But without anything else, let's thank Max one more time for that lovely talk. Okay, we can stop recording.